Hi, this is Dan Bullard with another instructional video, this time on sampling, aliasing, and Nyquist. I've been teaching sampling for years and years, and I understand aliasing better than most people in the electronics industry. So this time I'll try to show you how aliasing really works and why there are important constraints on sampling. We'll start with an overview of sampling. In order to sample, you must know the sampling formula. The ratio of the test frequency to the sample frequency is equal to the ratio of the number of cycles of the test frequency to the number of samples, or in math form, f sub t over f sub s is equal to m over n. In our formula, f sub t is the test frequency, that is, the waveform we're going to use to test our device or our circuit. F sub s is the sampling frequency, that is, how fast we're going to run the sampler. M is the number of cycles of f sub t. N is the number of samples. Let's start off with a really simple example. Here we have a single cycle of a 1 megahertz waveform and we want to capture 16 samples. In order to capture 16 samples of a 1 megahertz waveform in just one cycle, we're going to have to capture at what frequency? The answer is obviously 16 megahertz, since we'll have to run our sampler 16 times faster than the test frequency in order to capture 16 samples over just one cycle of the test frequency. Let's try changing our M to 2 now. So we're going to take 16 samples over 2 cycles of our 1 megahertz test frequency. Take a close look at the first cycle of the waveform. You can see there are 8 unique samples, but the second cycle has 8 samples that are identical to the first set. That makes that second set of samples redundant. In other words, if M and N are not mutually prime, and 2 and 16, that is an M of 2 and an N of 16, are not mutually prime, then some of the samples will be redundant. The true number of samples can be found by reducing the M and N ratio to the least common denominators. There is a reason to use redundancy, though, for waveform averaging, which can be used to reduce noise by taking multiple passes of the waveform. It separates the quantizing noise from other noise, and each doubling of samples reduces noise by 3 dB. So there is a benefit to using redundancy. There is a benefit to taking a redundant set of samples. You can reduce noise, which can be cheating if you're doing signal-to-noise measurements, but there are also many, many downsides, and that's really the point of this whole instructional video, to show you what the true downside is of using an M and N that are not mutually prime. Now let's see what happens when we change our M to 3. That is, we're sampling the same 1 megahertz signal. We're going to still take 16 samples, but we're going to do it by capturing 3 cycles of the waveform. So what will be our sample frequency? How fast do we have to sample in order to capture 3 cycles of the 1 megahertz signal instead of just 1 cycle? Well, if you do the math, and you do that by cross-multiplying, by the way, so 1 megahertz times 16 divided by 3 is 5.333 megahertz. So we actually get a slower sample rate if we can capture more cycles of the waveform. By the way, take a good close look at those 3 cycles of the waveform. You'll notice that all 16 samples here are unique. There are no redundant samples. So when M and N are mutually prime, you have no redundancy, and so you don't have the issues that we had before with an M of, say, 2 and an N of 16. Now let's try spreading our samples out even more. We'll capture 16 samples over 7 cycles of the 1 megahertz waveform, and the sample frequency calculates out to 2.29 megahertz. Recognize that every time M goes up, F sub S goes down, which is what you'd expect. Notice also that in this particular case, there's pretty close to about 2 samples per cycle. If you count it out in the first cycle, you'll find there's 3 samples per cycle, but in other cycles, there's only 2. So we're really close to having 2 samples per cycle, and Nyquist said something about that. Another guy named Shannon said something about that. You might not quite remember those, but we'll talk about that later. When M is about half of N, then you're going to have about 2 samples per cycle. Okay, we're going to keep pushing M up. So we're going to take our 16 samples over 9 cycles of the 1 megahertz waveform, and that makes our sample frequency drop down to 1.777 megahertz. Now our sample frequency isn't even twice what our test frequency was. And again, you might remember something about Nyquist or Shannon saying something about those things. And again, we have about 2 samples per cycle because M is about half of N. So the first cycle has about 2 samples, the second cycle has about 2 samples, the third cycle has about 2 samples, but look at the center one. The one cycle right in the middle has only 1 sample. So actually we have less than 2 samples per cycle. So we're disobeying some law that Nyquist or Shannon or one of those guys came up with. Okay, let's push M a little higher. We're going to take M all the way up to 15. So we're going to capture our 16 samples over 15 cycles of our 1 megahertz waveform. And we do the math and it comes out to a sample frequency of about 1.07 megahertz. Now looking at this, you might notice something very interesting. It looks as though our samples are describing a single cycle of the waveform but upside down. It's actually in reverse order. The samples are actually in reverse order of a single cycle waveform, and that's because M is just under N. Now take a wild guess at what happens if we push M to be 1 over N. So now with an M of 17, we get, again, a single cycle in our samples, but it's in forward order. So when M is just 1 over N, we get a forward ordered single cycle version of the waveform. When M is 1 under N, we get a backwards or inverted version of the waveform. Now back to the example of M equals 17, notice that our sample frequency is now below our test frequency at 0.94 megahertz. That is incredible. We're now sampling slower than our test frequency, and yet the signal is still visible. This is called aliasing. It's not really the signal, it's the alias of the signal. It's not exactly the signal that we were looking at. It just so happens that the samples fall in an order that makes it look like we're seeing the signal in a single cycle. This is one way of looking at aliasing, but there's a better way, looking in the frequency domain by performing an FFT. Passing a sample time domain waveform to a fast Fourier transform, otherwise known as an FFT, will result in the following. The resulting spectrum will contain n over 2 plus 1 spectral lines, also known as frequency bins. The spectrum will have a resolution of f sub t over m, or f sub s over n. Bin 0 will contain the absolute DC offset. Bin m will contain the peak amplitude of f sub t. The harmonics of f sub t will appear in multiples of bin m, and all other bins will contain any noise captured. With this diagram, I can describe what an FFT does for you. Across the top, you can see what appears to be 9 cycles of a slightly distorted sine wave that contains 512 samples, from sample number 0 to sample number 511. When we perform an FFT, we get a spectrum of the waveform containing n over 2 plus 1 spectral lines, also known as frequency bins, numbered 0 through 256. Bin 0 contains the amplitude of the DC offset. Bin n over 2 is called the Nyquist frequency, which is 1/2 the sample frequency, f sub s. This bin is not very useful, as you will soon see, so be careful not to allow any signal you care about to fall into this bin. Because the time domain version of the waveform contains 9 cycles of the waveform, in the spectrum we get the amplitude of the fundamental frequency at bin m, in this case bin 9. Any second harmonic energy falls into bin m times 2, or bin 18, because that is where f sub t times 2 would fall. Any third harmonic energy would fall into bin m times 3, or bin 27, because 3 times 9 is 27. You can imagine that this would be very useful for finding total harmonic distortion, otherwise known as THD, because all you have to do is set up a simple loop to scan the spectrum for any amplitudes and multiples of bin m, because harmonics of f sub t will be located in those bins. You can look for 2 harmonics, 3, 4, 5, however many you care about, simply by setting up a loop terminator to look at all harmonics up to the highest number you care about. Any noise captured in the time domain waveform will be spread across all bins, even the signal and harmonic bins. This is one reason to push n, the number of samples, as high as possible. More samples means more bins for the noise to go into, and the more accurate your signal measurements will be because there will be less noise per bin polluting the signal bins. Of course, the noise bins themselves are valuable. You can easily calculate the signal to noise level of this waveform by summing up the squares of the amplitudes of every bin except the signal and harmonic bins and taking the square root of the sum of the squares. That is your total noise. Zooming in near the fundamental bin, you can see the graininess of this spectrum. That graininess, or spectral resolution, is determined by how long it took to capture our sample set. The longer we capture, the finer the resolution. How long we sample, known as a unit test period, is determined by how many samples we take divided by the sampling frequency. The reciprocal of UTP is known as the Fourier frequency, and that controls our bin spacing. Also, of course, bin spacing is controlled by our test frequency divided by m, or the number of cycles. If you want very fine resolution in your spectrum, you'll have to set m very high for any given test frequency. Sampling your test frequency over a very large number of cycles will take a long time. The reciprocal of that time, UTP, defines the resolution of your spectrum. Want a 1 Hz resolution? Juggle the sampling formula to allow you to sample for 1 second. Want a 10th Hz resolution? Sample for 10 seconds. You can get any resolution you want as long as you're willing to wait for it. Of course, don't forget that better resolution may mean setting the number of samples to a very large number. And every one of those samples will have to be processed by a computer somewhere, and that could take a very long time indeed. Now that we know how an FFT works, let's take a look at an example waveform that I created. It has the fundamental in bin 1, because again, m is 1, and it has a third harmonic which squares up the waveform. Remember that a square wave is actually the sum of the fundamental, the third harmonic, the fifth harmonic, the seventh harmonic, the ninth harmonic. That creates a square wave. I've removed all but the third harmonic, so we have a squared up waveform. You can see in the spectrum I have an amplitude at bin 1, that is bin m, and in this case n is 32, and I have a smaller amplitude signal in bin 3, that is the third harmonic. That tends to square up the waveform. Now in my spectrum diagram across the top of the page, I showed that I'm going from bin 0 to bin 2 times n, or from the DC bin up to bin 2 times f sub s. But that's not really the case when you do an FFT. Remember, when you do an FFT, you only get bins 0 through n over 2. So that area from DC to f sub s over 2, that's called the Nyquist band, and you're not allowed to see anything beyond that. But I'm going to fake it a little bit and show you what happens in the higher frequencies and show you how aliasing really happens. Like we did before, we're going to push m up. So here we push m up to 2. We now have 2 cycles of the waveform, which means that when we do the FFT, the fundamental goes into bin 2. But that also causes the third harmonic to go up to bin 6. So the third harmonic moves up at about 3 times the rate as the fundamental. We'll have to watch out for that. Now we push m up to 3, meaning that we have 3 cycles of the waveform. The third harmonic, however, is now up in bin 9. Now we push m up to 4, so now the fundamental appears in bin 4 of the spectrum, and of course the third harmonic shows up in 4 times 3, or bin 12. It seems like we're going to be in trouble if m goes up any higher, because then the third harmonic will go beyond bin n over 2 and will disappear. Now we push m up to 5, which means that the third harmonic is in bin 15, right on the edge of the Nyquist bin. Remember that our n is 32 in this case, which means that n over 2 is 16, so the Nyquist bin is in bin 16. So if m goes up any higher, we're going to lose the third harmonic. It's going to leave the Nyquist band. Now we push m up to 6, and look what happened. The third harmonic went up to 3 times 6, or bin 18, which is higher than bin n over 2. And in its place, we got an alias, which is at a different place, but it represents the amplitude of the third harmonic. It's just that it's in the wrong place, which makes it an alias. So because the third harmonic has moved beyond the Nyquist band, it's in bin 18, but our Nyquist band only goes from bin 0 to bin 16, then what bin is the alias in? Well, luckily you've got Dan's rules to work it out. I developed these rules on my own. They specify how you can tell which bin the alias went to. The diagram at the top shows the Nyquist band from DC to f sub s over 2, also DC, or bin 0, to n over 2. That's where the Nyquist band is, and that's all you ever see when you do an FFT. Beyond the Nyquist band are other frequencies, but we just can't see them in the spectrum when we do our FFT. But anything up in those areas will show up in the Nyquist band. So as the note says there, anything that appears in these bands folds back into the Nyquist band. They fold back, and you may have heard of that term. So anything that appears in these areas that's invisible will appear in the Nyquist band. And that's the problem. Anything that appears up in this area will fold back into the Nyquist band and pollute it and make it difficult for us to sort out which thing is which. Okay, I only have two rules. Dan's aliasing rule number 1 says if the bin is greater than n, then the bin is equal to bin modulo n. Modulo is the remainder operator, so in our case the answer to this question is no. In other words, is 18 greater than 32? The answer is no, so we don't calculate the modulo operator yet. The next rule says if the bin is greater than n over 2, bin is equal to n minus bin. In other words, is 18 greater than 16? And the answer is yes. So what does that mean? That means that we calculate our alias by calculating n minus bin. So what is 32 minus 18? 32 minus 18 is 14. So going back to the original diagram, well, you can see that our third harmonic is 2 steps above 16. Our alias is 2 steps below 16, and that's what's meant by folding back. It actually bounced off of the Nyquist frequency, or folded over, folded back. So 2 steps above n over 2 becomes 2 steps below n over 2, so our alias happens at bin 14. Okay, let's see what happens when we push m up to 7. So the fundamental is in bin 7. That means the third harmonic is in 7 times 3, or 21. But again, 21 is not in the Nyquist band. And you can see the alias, but what bin is it in? So back to Dan's aliasing rules. Dan's aliasing rule number 1 says if bin is greater than n, then bin equals bin modulo n. Is 21 greater than 32? The answer is no, so that one doesn't apply. Dan's aliasing rule number 2 says if bin is greater than n over 2, bin equals n minus bin. That one is true, so the alias is going to be in bin 11. So now, if we go back to the original diagram, you can see that while the fundamental is in bin 7 and the third harmonic is way up in bin 21, the alias of the third harmonic is down in bin 11. So as we keep pushing m up, the fundamental will keep going up, the third harmonic will keep going up, but the alias of the third harmonic will keep going down. So as we take m up to 8, notice that the fundamental is in bin 8, the third harmonic is in 3 times 8, or bin 24, and the alias of the third harmonic appears to also be in bin 8. Now that's a problem, and that's why m and n must be mutually prime. In this case, m is 8 and n is 32. They have a common divisor, 2. If you do that, look what happens. The amplitude of the fundamental is now in bin 8, and the amplitude of the third harmonic's alias is also in bin 8. They're going to cancel each other out to some degree, and that's the real reason why you don't want common divisors between m and n. Let's go back to Dan's aliasing rules just to make sure we understand how they work. Again, rule number 1 says if bin is greater than n, bin equals bin modulo n. Is 24 greater than 32? That is, the third harmonic of the fundamental, 3 times 8 is 24. So is 24 greater than 32? The answer is no. So then, is bin greater than n over 2? Yes, it is. 24 is greater than 16. So 32 minus 24 is 8. So the third harmonic will fall in bin 24, but the alias of the third harmonic will fall in bin 8. Unfortunately, that bin is already occupied by the fundamental. Now, the amplitude of the fundamental is being corrupted by the amplitude of the alias of the third harmonic. That's why we can't have common divisors between m and n. Now earlier we talked about reducing m and n to common divisors. So here we have an m of 8 and an n of 32, but they have a common divisor, 8. So we can reduce it to an m of 1 and an n of 4. That's an effective n of 4. So that means out of our 32 samples, only 4 samples are unique, the rest are redundant. So the second 4 samples are redundant to the first, the third 4 samples are redundant to the first, and so on. That means that our number of bins is not what we think it's going to be. Normally the number of bins is equal to n over 2 plus 1. So we would assume that we would have 16 unique bins plus the DC bin. But in fact, the number of effective bins, in this case, because our effective n is 4, our number of effective bins is 4 divided by 2 plus 1, or 3. So there are actually only 3 bins for things to go into. DC, that is bin 0, the fundamental bin, which will be bin 8, and then the Nyquist bin, which is bin 16. There's no place else for any of the signal amplitudes to go. Now we're already in trouble with a waveform that has only 2 signals, the fundamental and the third harmonic. But imagine it was a square wave or some other strange waveform with more harmonics. What would happen? Remember, there's only 3 bins where things can go. So in this chart we're showing that f sub t goes in bin 8. The second harmonic, if there was one, would go into bin 16. The third harmonic we know already goes in bin 8, and that's already occupied. I showed that as red to show that it interferes with f sub t. The fourth harmonic would go into bin 0. Oops, that's a problem because now we don't really know what our DC offset is if there is a fourth harmonic. The fifth harmonic falls into bin 8, the sixth falls into bin 16, the seventh goes into bin 8, and so on. The problem now is we've only got really 3 unique bins for things to go. Any harmonics will corrupt virtually anything in our spectrum. So you want to avoid using an M and N that have common divisors. That is, you want mutually prime M and N. But some people take that to mean that you need M to be prime. That's not the case. Here's an M that is not prime, an M of 9. Let's see what happens. With an M of 9, we end up with the fundamental in bin 9 and the third harmonic falling in bin 3 times 9, or bin 27. We can see in this diagram the alias of bin 27, the third harmonic, falling back in the Nyquist band, but it doesn't seem to have fallen on top of the fundamental. But let's figure out where it went and why. So back to Dan's aliasing rules. Again, rule 1 says, is bin greater than n? Is 27 greater than 32? The answer is no. So, on to rule number 2. Is 27 greater than 16? Yes, it is. So we calculate 32 minus 27, which equals 5. So that's where the third harmonic went. It aliased back into the Nyquist band into bin 5. So our third harmonic aliased back into the Nyquist band, but didn't fall on our fundamental, and that's a good thing. But could there be other harmonics that fall onto our fundamental? M is not prime, but it is mutually prime with n. Does it have to be prime? Let's take a look at another chart. Here we show our M is 9. Bin 9 is where the fundamental is, f sub t. The second harmonic, if there was one, falls into bin 14 after obeying Dan's aliasing rules 1 and 2. The third harmonic, we know that falls in bin 5 after we go through Dan's aliasing rules 1 and 2. If there was a fourth harmonic, it would fall in bin 4. So far, none of them had fallen back into bin 9. If there was a fifth harmonic, it would fall into bin 45, and then Dan's aliasing rules show that it would drop back into the Nyquist band into bin 13. Again, nowhere near bin 9. The sixth harmonic would fall in bin 10, the seventh harmonic would fall in bin 1, the eighth would fall in bin 8. So far, no repeats. The ninth harmonic would fall in bin 15, and so on and so forth. Notice that there are no repeats. In these charts, when there are no repeats, the text for the bin is in black. So everything falls in its own unique bin as long as M and N are mutually prime. But M is not a prime number, and still we don't have any repeats in our bins. So M doesn't need to be a prime number, it just needs to be prime relative to N. Okay, let's take M up to 10. Now with an M of 10, the fundamental drops into bin 10. The third harmonic, you can see it way up there around bin 30. So it will alias back into the Nyquist band somewhere. You can take a wild guess, but it looks like bin 2, but let's find out. So, first question, is bin greater than n? 30 is not greater than 32, so no. Is 30 greater than 16? Yes, so Dan's aliasing rule number 2 takes effect. 32 minus 30 is 2, so yes indeed, that alias did fall in bin 2. Now, 10 is not a prime number, and it's not mutually prime with n. So let's talk about reducing m and n again. So with an m of 10 and an n of 32, we reduce that down to an m of 5 and an effective n of 16. We still have 32 samples, but the first 16 will be unique, the second 16 will be redundant. Now we know our number of bins will be n over 2 plus 1, so our number of effective bins will be 16 over 2 plus 1, or 9. So back to our chart of harmonics. F sub t falls in bin 10. If there was a second harmonic, it would fall into bin 20, but bin 20 is beyond bin 16, so that'll alias back into bin 12. The third harmonic, we already know, went out to bin 30, and that aliases back into the Nyquist band into bin 2. The fourth harmonic drops into bin 8. The fifth harmonic goes into bin 14. The sixth harmonic goes into bin 4. The seventh harmonic goes into bin 6. And the eighth harmonic goes into bin 16. Now notice the ninth harmonic also goes into bin 6, just like the seventh harmonic did. Those colors match. The 10th harmonic would fall in bin 4, but we already have something in bin 4. That's where the 6th harmonic would go. The 11th harmonic would fall into bin 14, but the 5th harmonic went into bin 14. The 12th harmonic would go into bin 8, just like the 4th harmonic did. So the problem here is there's not enough bins for all these harmonics. That's because m and n are not mutually prime. And we lost all of our odd numbered bins because we had redundant samples. Now let's push m up to 11. So f sub t goes into bin 11. The third harmonic goes up into bin 33, 3 times 11. You can see the alias of the third harmonic down in bin 1, but let's calculate and see how that works. So back to Dan's aliasing rules. Rule 1, is 33 greater than 32? Yes. Finally. So 33 modulo 32 is equal to 1. In other words, if you take 33 and subtract 32, the answer is 1. If the answer was still greater than 32, you would subtract 32 again, and subtract 32 again until the result is less than 32. Then that is the remainder. So the modulo is simply taking the remainder of a division. Now we still have to run through rule number 2. Is 1 greater than 16? The answer is no, so we don't have to apply it. So Dan's aliasing rule shows that when the third harmonic goes into bin 33, 1 above n, it aliases back into the Nyquist band at bin 1, that is 1 over the DC bin. For the foreseeable future, as m increases, the alias of the third harmonic will move up towards n over 2. And when it gets to a certain point, it will bounce off of n over 2, the Nyquist frequency, and work its way back down towards DC. Then it'll bounce off of that and work its way back up to n over 2. So it will basically bounce back and forth in the confined space called the Nyquist band. Now that's true not just for the third harmonic, but for everything that we sample. Everything that's captured by our sampler will end up in the Nyquist band. So we move m up to 12, and now you can see the third harmonic working its way up towards n over 2. An m of 12 means common divisors between our m and our n of 32. That's a problem, and if you look at the time domain version of the waveform, you can see there does appear to be some redundancy in the samples. Basically, large portions of the waveform look like repeats. Okay, let's figure out where our third harmonic went. Our third harmonic at 3 times 12, or 36, is 36 greater than 32? The answer is yes. So 36 modulo 32 is 4. Is 4 greater than 16? The answer is no, so the new bin number for the alias is bin 4. Because 12 over 32 can be reduced to 3 over 8, our number of effective bins is now 8 over 2 plus 1, or 5. With only 5 bins in the Nyquist band for things to go into, it gets crowded fast. F sub t goes in bin 12, the second harmonic, if there was one, goes into bin 8, the third harmonic, we already saw, goes into bin 4, the fourth harmonic goes into bin 16, and there's only one left, bin 0, where the DC goes, and the 8th harmonic will be polluting that. So if m and n have common divisors, it's a disaster. Your harmonic products end up all over the place and piling on top of each other, polluting each other, and making their measurements totally inaccurate. So let's move m up to 13. Now the third harmonic is way up there, 3 times 13, or 39, and the alias of the third harmonic is working its way up from the DC bin up towards n over 2. So where did the third harmonic go? Well, is 39 greater than 32? Yes. So 39 modulo 32 is equal to 7. And since 7 isn't greater than 16, we don't have to implement rule number 2. So the third harmonic aliases back to bin 7. As M moves up, the fundamental moves up, the alias of the third harmonic moves up at the same time, but 3 times faster. So where did the alias go? Back to Dan's rules. 3 times 14 is 42. The problem, of course, is that 42 is not in the Nyquist band. So where does it go? Is 42 greater than 32? The answer is yes. So 42 modulo 32 is 10. That was easy. Is 10 greater than 16? The answer is no. So the answer is 10. So the third harmonic aliased all the way back from bin 42 down to bin 10. When we move M up to 15, you see something very interesting in the time domain. The time domain waveform has a very strange shape, and that is due to the fact that we are currently at just about 2 samples per cycle. Nyquist stated that that was the minimum, 2 samples per cycle. You can't transmit any information without at least 2 samples per cycle. Now, that doesn't mean that you can't alias. He didn't outlaw aliasing. He simply said to transmit data, you must have 2 samples per cycle. So with an M of 15, our fundamental is in bin 15, just one below n over 2. Our third harmonic is way up in bin 45, but we can see its alias back in the Nyquist band, so again, let's go find out where it is. Is 45 greater than 32? Yes, so 45 modulo 32 is 13. Is 13 greater than 16? No, so we don't have to apply that rule. So our third harmonic is aliased all the way back from bin 45 into bin 13, and that's pretty clear when you look at the frequency domain plot of this waveform. Now 15 is not a prime number, so let's take a look at where the harmonics would go if there was more than just one harmonic here. Again, F sub t falls in bin 15. The second harmonic, which would be bin 30, drops back into bin 2 when it aliases. The third harmonic, we already saw, goes from 45 to bin 13. The fourth harmonic, if there was one, would alias back down to bin 4. The fifth harmonic, which would be in bin 75, would alias back down to bin 11, and so on. Notice, no repeats. Every harmonic has its own bin and never falls on top of any other harmonic or on top of the fundamental. So M does not have to be prime. M must be mutually prime with N, and that's the only requirement. Now we push M up to 16, and it's pretty obvious this is not going to go well. With M on the Nyquist frequency, it's virtually invisible. You can't trust it at all. You can see in the time domain representation of the waveform, there is no signal amplitude. That's because the signal amplitude depends entirely upon the phase of the waveform. Unfortunately, our exact 2 samples per cycle fell at both 0 degrees and 180 degrees. And with a sine wave, the amplitude is at 0 degrees, and the amplitude is at 0 at 180 degrees. Bin 16 is not to be trusted because the phasing of the waveform controls what the amplitude is going to be. With an M of 16 and an N of 32, we reduce to 1 over 2, which means our number of effective bins is equal to 2 over 2 plus 1, or just 2. So there's only 2 bins for things to go into, no matter how many harmonics we have. So even if we had an impulse with an M of 16, every single harmonic that we got would end up in either bin 0 or bin 16. And because they would all be piling on top of each other, we couldn't tell what our DC offset is or what any of the harmonic amplitudes were. Now when we take M up to 17, look what happens to the fundamental. It's now gone above n over 2, which means it has an alias at n over 2 minus 1. The third harmonic has gone way up, and now of course it's aliasing back down into the Nyquist band very close to the fundamental. So by now you're probably pretty good at this, but let's go ahead and go through it. Is 17 greater than 32? The answer is no. So is 17, the fundamental, greater than 16? Yes. So 32 minus 17 is 15. So that's why the fundamental appears in bin 15. The third harmonic is way up in bin 51, which again we can't see because we can't see anything outside the Nyquist band. So 51 is greater than 32. So 51 modulo 32 is 19. But 19 is still higher than 16, n over 2. So 32 minus 19 is equal to 13. So the third harmonic ends up in bin 13, while the fundamental ends up in bin 15. Moving M up to 18, you can see that both the alias of the fundamental and the alias of the third harmonic are working their way back down towards DC. The fundamental aliases back down into bin 14, while the third harmonic, which ends up way up in bin 54, which again we can't see, aliases back down to bin 10. Now it should be pretty obvious that 18 is going to be a problem because it reduces to 9 over 16, so our effective number of bins is actually only 9. So there's only 9 places for things to go, and you can see in our harmonic chart there's a lot of repeats, and there's nothing that can be done. Don't use an M and N that are not mutually prime. Let's push M up to 19 now and watch where the aliases of both the fundamental and the third harmonic go. The fundamental is still not greater than N, so then the question is 19 greater than 16? The answer is yes, so we alias back into bin 13 for the fundamental. The third harmonic, however, is way up in bin 57, which again we can't see, so it's greater than 32, so it's now aliasing back into bin 25. However, we can't see bin 25 either, so we have to apply Dan's aliasing rule number 2. Is 25 greater than 16? Yes. So 32 minus 25 is equal to 7. So the third harmonic is aliasing back into bin 7. Now we take M up to 20, which means that the fundamental is aliasing and the third harmonic is all the way up in bin 60, very close to 64, which is 2 times N. So our fundamental aliases down to bin 12, the third harmonic aliases down to bin 4, and we knew that was going to happen because with an M of 20, we know there's common divisors between M and N. Our effective number of bins now is 5, and so you can see there's only 5 places where things can go, so if there are any harmonics other than the third harmonic, they will end up falling on top of the fundamental, as well as the DC bin, as well as the Nyquist bin, and we already talked about the fact that the Nyquist bin is unreliable. With an M of 21, our fundamental aliases back into bin 11, and our third harmonic aliased all the way back from bin 63 down to bin 1. Now 21 is not a prime number, but it doesn't have to be. It only needs to be prime relative to N. Every harmonic has its own bin to go into, and there are no repeats. Pushing M up to 22 shows something interesting. The third harmonic has disappeared from our little diagram here, but that doesn't mean it's gone. I just didn't extend the diagram beyond 2N. The third harmonic did fall back into the Nyquist band. Looks like it fell into bin 2. Let's see why. The fundamental alias is back down into bin 10. The third harmonic alias is back down to bin 2. Just because my diagrams stop at 2 times N doesn't mean that everything stops at 2 times N. The frequencies go on forever. Anything that gets captured can and will alias back down into the Nyquist band. Pushing M up to 23 means that our fundamental will alias back down to bin 9, and the third harmonic will alias all the way back down to bin 5. With an M of 24, you can tell there's going to be trouble. The fundamental will alias down into bin 8, and so will the third harmonic. And the effective number of bins is only 3, so there are only 3 places where things can go. The DC bin, that's a no-no because that's where our DC offset is supposed to go. Bin 8, that's okay, and then bin 16. That's bad because it's very sensitive to phase. Anything in the Nyquist bin is unreliable, so don't count on the Nyquist bin for any testing. An M of 25, on the other hand, is just fine, even though 25 is not a prime number. The fundamental alias is back down to bin 7, the third harmonic alias is back down into bin 11. With an M of 26, our fundamental is going to alias down into bin 6, and our third harmonic is going to alias down into bin 14. Here I've expanded the modulo operator, showing that 78 minus 32 is 46. 46 is larger than 32, so 46 minus 32 is 14, and then is 14 greater than 16? No. And of course 26 over 32 reduces to 13 over 16, so we end up with only 9 unique bins. Pushing M up to 27, you can see how the fundamental aliases back into bin 5, and how the third harmonic aliases back down into bin 15. Again, I expanded the modulo operator, so the third harmonic goes in bin 81. 81 is greater than 32. 81 minus 32 is 49. 49 is still larger than 32 though, so 49 minus 32 is 17. That's smaller than 32. Now, is 17 larger than 16? Yes. So 32 minus 17 is 15. The third harmonic ends up aliasing into bin 15. Here's another suspect M at 28. Our fundamental is going to alias down into bin 4. The third harmonic is going to alias down into bin 12, and 28 over 32 reduces down to 7 over 8, which means we're going to end up with only 5 unique bins. We push M up to 29, the fundamental ends up aliasing back into bin 3, and the third harmonic, which is not even visible on our chart anymore, aliases back to bin 9. Now that we know that our fundamental aliased into bin 3, take a look at the time domain representation of the waveform. Notice it's 3 cycles, just as though M were 3, except rather than starting positive, they're going negative. So it's 3 cycles negative going, which means they're out of order, they're reverse order. So with an M of 29, our waveform was sampled as though we were sampling with an M of 3, except in reverse order, because the fundamental is 3 bins down from bin N. This is aliasing at its best, and it is useful this way. Notice now the alias of the third harmonic is in bin 9, just as though M were 3. So the third harmonic being in bin 9 works just the same as if the M was 3 or if the M is 29. When we push M up to 30, take a look at the time domain waveform. We have 2 cycles of the waveform, just as if M were 2. And that's because M is actually 2 below N. And so they're 2 cycles of inverted waveforms because they're captured in reverse order. And you can see that the fundamental aliased back down to bin 2 and the third harmonic aliased back into bin 6. Here we use Dan's rules to prove that the fundamental aliased down to bin 2, and here the third harmonic aliased back down to bin 6. This is just exactly the way it would be if M were 2. The third harmonic would then be in bin 6. Now we push M up to 31. Take a look at the time domain waveform. It's exactly 1 cycle, but it's in reverse order. The reason it's 1 cycle is because M is 1 below N. The alias falls back in bin 1, so the waveform looks like M was 1, except in backwards order. The third harmonic has alias back into bin 3. When M is N minus 1, you get an M of 1, but in reverse order. Here I show how Dan's rules predicts that the alias of the fundamental will fall back in bin 1, and here I show how the alias of the third harmonic will fall back in bin 3. And it's not just the fundamental and the third harmonic that behave that way. The fundamental falls in bin 1, the second harmonic aliases back into bin 2, the third harmonic aliases back into bin 3, the fourth harmonic aliases back in bin 4, the seventh harmonic aliases back into bin 7, and so on. So using an M that is N minus 1 is just like using an M of 1, except that the time domain version of the waveform is reversed. The phase is not correct, but who cares? An M of 32 is obviously going to be a disaster, but let's find out why. Dan's aliasing rule number 1. Is 32 greater than 32? The answer is no. Dan's aliasing rule number 2. Is 32 greater than 16? Yes. So the result is 32 minus 32, or 0. So the fundamental falls in bin 0. So does every other harmonic. And what's worse is that there's only 1 bin for everything to go into. The fundamental and every harmonic ends up aliasing back into bin 0. Now that you have a better idea of how aliasing works, let's watch a high-speed version of what we just went through. I hope you now know more about sampling, aliasing, and Nyquist. Don't forget Dan's rules, and be sure to visit me at www.danbullard.com. Thanks for watching.